and thank you very much for coming to my talk entitled Generative Deep Learning, the Key to Unlocking Artificial General Intelligence. It's a real honor to be speaking here at OpenConf. Thank you to all the people involved for inviting me here today. It's such a shame, obviously, I couldn't be in Greece to give this talk. It's raining really hard here in London at the moment, and believe me, I would much rather be giving this to you all in person. So hope maybe another time we'll all get to meet each other. But again, thank you very much for joining us today. This talk, as I say, is about generative deep learning, a subject that is very close to my heart. I've written a book recently on the topic entitled Generative Deep Learning, published by O'Reilly. It's come really as a result of lots of my own research into the field, but also the kind of public interest really in the subject. I think over the last 5 years, it's something that really has grabbed the public's attention and also the attention of people in the field because of its recent progressions and the amazing advancements that have been made with images, music, text. It really has boomed recently. And so, yeah, the book is really a summary of the different kinds of generative deep learning that exist. And this talk is an accompaniment to that book, which will go through some of the key ideas behind what generative deep learning is, as well as talking more generally about why I feel it's a real key to understanding what intelligence is. So it's not just, for me, another branch of machine learning, but it's something that gets right to the heart of what we mean for a machine to be intelligent. I'm also co-founder of a company called Applied Data Science. We're a data science consultancy here in the UK, and we work on a range of projects from machine learning to all different kinds of data science topics. So please do check us out. But as I say, I'm here today to talk about the subject of generative deep learning, which is something unfortunately we don't get to do much of in our roles as data scientists, but certainly in my spare time is something that I've enjoyed learning about and putting together the book for. So just a quick summary of what we're going to be talking about. So I want to assume no kind of background in deep learning or machine learning to begin with. So we'll just have a quick summary of what it means to build a generative deep learning model. We'll then go into what I think is one of the most important models out there, which is the Variational Autoencoder, and especially for people who haven't seen the concept before, this is a really great way to start learning about it. So we'll talk about that, and then we'll start progressing into more advanced topics like world models, which is something that actually uses a variational autoencoder but in a reinforcement learning setting, and then that will lead us nicely onto this topic of AGI, artificial general intelligence. And it's a really broad subject, obviously, and one that we're only minutely along the path of understanding. But I kind of just want to have a general open discussion here, even though I'm kind of on my own talking to my computer. But hopefully afterwards we'll have a time to have some questions about the field and where this might go in the future. So first of all, then let's start talking about generative deep learning. So first of all, the definition, dictionary definition, if you like, of generative modeling is that it tries to create new observations that may have been sampled from a training set, rather than trying to classify observations that you already have as part of a test set. So for example, a typical supervised learning problem would take a set of images, such as these seen on the left here, and try to classify them in some way, maybe male or female, or happy or sad, blonde hair, dark hair, etc. Well, a generative model tries to do something even more than this. It tries to create a new image entirely. So we don't have any label here, but what we do have is a set of training data that we can try to mimic and try to copy. And you can see on the right here, this is an example of style GAN, which is one of the most famous examples of a machine learning, a generative deep learning model. And you can see here that not only is it able to create new kinds of face that might be possible, but it does so in a continuous fashion. And this is really the key idea behind generative modeling, is that we often try to embed the generated faces or the generated whatever they might be, the objects, into a latent space where we can move fluidly between different objects of generation, and ideally we can sample from this distribution as well in order to generate new samples. So what we're going to do in this talk is just go through some of those core ideas and talk about how this might be possible, hopefully from first principles. So, I mean, as I say, this is a field that has come on an incredible amount in the last 6-7 years. I mean, you can see on the left here, this is an example of what was possible in 2014. And then today and beyond, we're at state of the art, where it's almost impossible now to tell the difference between what's generated by machine and what's generated by real life. And you can see the progress has been quite stark, both in terms of the quality of the image, but also in terms of the ability of machines to be able to generate things that would perhaps be considered as creative. So a good example of this is GPT-3, which has come out, and it's a text generation algorithm effectively, where it's not just creating things that are grammatically correct, but it creates concepts and ideas within its output that you almost stop and think, wow, that's incredible that a machine can link ideas across paragraphs and across different sentences. So it's less now generative modeling about trying to create things that look correct, but more things that feel human. And that's really where the field is progressing now, is that we've kind of, like, in terms of images and faces, we've kind of solved the problem of creating a face that looks accurate. And we solved the problem of creating words that are grammatically correct together. But now the problem's starting to, from 2020 and beyond, starting to be more about how do we create things that are truly fooling humans when it comes to actual content creation. And GPT-3, for example, has been used for lots of things, including actual copy creation on websites. So if you need to create 100 examples of a particular paragraph of text and test them all, then GPT can start to do that for you. So it's really been a quite exciting time to be involved in this. And I want to start by, as I say, going from first principles and sort of just really embedding and hopefully sharing with you what a generative model is, because it's often quite difficult to grasp the core concepts behind the field. So here we have a set of points in 2D, and if I were to ask you to come up with a way of generating new points that look as if they've been sampled from this set, there's a few ways you could do this. You could, for example, draw a rectangle around all of the points that have been created so far, and simply say, well, I'm going to choose points at random, a uniform distribution over this rectangle, and I'm going to give 0 probability to points outside this rectangle. And congratulations, that is your first generative model, because you have a distribution over which you can sample to generate new points that look as if they belong to the training set. So this is probably the most basic example of a generative model you could think of, and it's certainly not very impressive, but it is drawn from the data. We've estimated parameters on the bounds of the rectangle, which can be parameterized by the x1 values and the x2 values of those boundaries. And it satisfies the criteria as well of being able to be sampled from, which is a really important aspect of any generative model. Now, there's some ways that this model might be incorrect. For example, if I were to show you how this data was actually generated over a uniform distribution of the world map, then we can see that our rectangle has got it wrong in some places. In other words, if we as humans truly instinctively understood where the data was being drawn from, then we would see, for example, that some points in the middle of the sea, instinctively we would understand that those weren't points from the data generating distribution, but our generative model would have put points in the sea. And similarly, there are some points, for example, in Alaska, up in the top left there, which our generative model would have never been able to generate because they lie outside the rectangle. And so the point I'm trying to make here is that these two distributions, the generative model itself and the true data generating distribution, we are essentially trying to make them as similar as possible. We are trying to make these two distributions identical if possible, but this is very difficult because we obviously don't know the true data generating distribution. We don't know, for example, what makes a face mathematically. We just instinctively know that it looks like a face. So we have to come up with some way of making a model, this P model here, accurately reflect P data without actually having access to P data. And so why is this difficult? Well, you can imagine here a space of all possible things that could be drawn in a 1024 by 1024 grid of pixels is absolutely enormous. Obviously, you're multiplying those two dimensions together, and then you're also multiplying by the number of dimensions in a particular pixel, which is 3 for an RGB value. And this is just the dimensionality of the space. So if you basically multiply these together and then realize that any pixel can take one of those values, then you obviously end up with an enormous number of possibilities, most of which are just random noise and very, very few are actual faces. So this is one of the key reasons why generative model is very different. It's very difficult in high dimensions. The other things I just wanted to mention briefly are obviously that there's this complex conditional dependence between features which you see in images. A green pixel over the top left of the image may be the background, for example, if they're standing in a forest. That also has to match the same as the top right of the image, for example, to be able, as humans, for us to understand that this is a continuous background that they're standing in front of. But for a model to connect those two when they are spatially extremely far apart isn't easy. And it's one of the real challenges of deep learning, of generative modeling, I should say. And the other reason it's difficult is because of this sparsity, like I just mentioned. Yeah, I mean, it's easy to build a generative model in a few dimensions because there's actually only a few things that you need to check over, but obviously in millions and millions of dimensions, it's a much tougher problem. And the key concept that solves both of these problems, happily, is deep learning. And that's where all, I would say, of the major advancements in generative modeling have been made in the last 5 to 6 years, has been in deep learning frameworks. So we're going to explore one of those right now, called a variational autoencoder. And again, we're going to go from first principles on this with a toy example. So I want you to imagine, first of all, that this is a set of data that you've been given, and you've been asked to generate a new image that belongs to the set. For humans, this is really easy because we can immediately see that there's two dimensions that matter here. There is the width and, in fact, the depth of the cylinder, and there's also the height. So those are the two dimensions over which this data set can be defined. So what we're doing instinctively is we're taking the image, this cylinder here, and we're mapping it into a latent space in our heads of two dimensions, one of which is the height along the y-axis here, and then one of which is the width along the x-axis. And we instinctively understand that all possible points in this latent space are physical cylinders that could be created, and that we only have access to some of the data from this latent space, which are the filled in examples here. But the real amazing thing that we can do as humans is that we can decode each of these points in the latent space back into the pixel space instinctively. And that's what the blue dot here is showing, is that we can take a point, any point in this latent space, and decode it back into a cylinder. And so what we'd ideally like is we'd like a model to be able to do this for us. And that is indeed what an autoencoder allows us to do. It's two halves of the same coin, if you like, one of which encodes the pixel space of the cylinder into a latent space, which in our case that we just saw was in two dimensions, and then a decoder on the right hand side, which simply takes points in the latent space and decodes them back into pixel space. The challenge here is, how do you train one of these models? How do you make sure that the encoder can do its job and the decoder can do its job in a suitable way? Well, both of these encoders and decoders are neural networks, so they are effectively layers of nodes which are connected by weighted edges with nonlinearities. And to train a neural network, you need a loss function. You need to tell the neural network how it's doing and how well it's performing at a particular task. And so what we'd like this autoencoder to do is to be able to take a cylinder on the left-hand side, push it through the encoder into the latent space, and then the decoder to pick up that single point, which in our case is in 2 dimensions, and map it back into pixel space as best that it can. And therefore our loss function, essentially our ability to tell the model how well it's doing, is just simply the root mean squared error between the starting image and the end image. So you take every single pixel and you work out what the root mean squared error is between those 2 points. If you sum over all of that, then you get the root mean squared error, obviously after taking the square roots. So what we're trying to do here is minimize this. We want these 2 images to be absolutely identical if possible. So we'd like to get this as close to 0 as possible. And if you do that, if you train a model to do this, you get something that looks a little bit like the diagram on the bottom right here. So I've used the MNIST dataset, which is fairly common. It's a set of handwritten digits. And what this shows is the latent space in 2 dimensions if you train an autoencoder to try as best as possible to autoencode each of the MNIST digits. So what you can see here is that every single image in the dataset is a point in this plot, and I've coloured it here by the label on the image. Obviously, the label wasn't used during the training, but it's quite nice to see that the autoencoder has managed to place all of the 1s together and all of the 2s together, and so on. So it obviously has a good understanding that placing like things in the same point in the latent space is probably a good idea, because the decoder needs to obviously take this information and try to map it back to the original pixel space. But there's a few problems with this autoencoder on its own. Firstly, the sample space here is really poorly defined. And what I mean by that is that we would find it difficult to sample very well from this 2D plane because, well, what's to stop us sampling the point a million? They just happen to be clumped roughly between sort of -10 and 30, and -30 and 10 on the y-axis. But what's to stop us sampling a point that's quite far away from this? What would we get? So there's not really a good definition of how to sample in this space, other than saying, well, you can pick any point, but then we're not really guaranteed to get something interesting. And then secondly, the other problem is that local continuity isn't guaranteed. You can see here 3 examples of points where I've kind of chosen points that sit either between 2 groups or slightly outside the clusters of points, and we get fairly sort of blurry, not very well defined digits that would be quite hard to sort of say, yes, this is a good example of a generative model that can produce any new digit. So if we decode these points, we don't get things that are very, very satisfying to look at and look like they've been drawn from MNIST. So the solution here is something called a variational autoencoder, which is a proper generative model that solves these problems in a simple way. It simply says, well, instead of encoding everything to a single point, why don't we encode it into a small normal distribution, so that the decoder, instead of just decoding each point singularly, it instead samples from this normal distribution and then decodes that point instead. And what this does is it has the effect of essentially ensuring that any region around the normal distribution where the image has been located has to naturally be continuous. It has to decode to roughly the same thing, because obviously the decoder could choose anything around this normal distribution in order to produce the image on the right hand side. So by making this almost like fuzzy in the middle, it actually strengthens the model, because it means that we now just don't have a set of individual points, but we have groups of normal distributions, which ultimately makes this local continuity problem go away. So we now need to tell the model in the loss function that we'd like it to do this, and we ideally need it to center these normal distributions as much as possible around the standard normal, because then that means that we have an easy ability to sample from this distribution and therefore generate new kinds of images. So we do that using something called the KL divergence, the Kublai-Bleck, get my tongue around that. Well, I'll just call it the KL divergence. So that essentially tells you the distance between this standard normal and any one of these encoded normal distributions in the latent space. And we'd like that to be as small as possible. So in other words, we want this to be as much as possible just encoding things into standard normals, because that way we essentially crush everything towards the origin. We try to keep this as tightly compacted as possible, but obviously not so tightly compacted and not so similar to standard normals that the root mean squared error is very large. So the overall loss function is simply the root mean squared error plus the KL divergence. So what this does is it has the effect of, as I say, moving everything much more towards the origin. On the left-hand side, you can see that the points now are being encoded into what looks very much like a standard normal distribution, obviously multi-dimensional, two-dimensional in this case, centered around the origin. Indeed, if we kind of make this into p-values instead of z-values, we can see that the space has been filled very uniformly as much as possible, and there's not so many gaps here between the distributions, between the different numbers. So if we now sample, you can kind of imagine here moving around the latent space, if you can imagine a point kind of moving around, we can see that there's nice local continuity, and we get this smooth transition between all of the numbers. So that at any point you could stop this and justifiably say that this is a number from the MNIST dataset, even though most of these or all of these images in fact won't have been in the MNIST dataset, because they're points that have been drawn at random from the latent space. So this is an example of our first generative model. It's a variational autoencoder. It's simple in the sense that it's essentially a neural network that's mapping data set into a latent space and then decoding that data set. But it has profound implications for lots of different areas, including reinforcement learning. And this is one of the areas I wanted to talk about today, is how it's used in something called a world model, which is a paper from David Haar and Jürgen Schmidhuber from 2018, which showed how you can use a generative model inside a reinforcement learning algorithm, which actually strengthens it. And I think this is a really exciting development. So first of all, if you haven't heard of reinforcement learning, this is simply one of the branches of general machine learning and AI that tries to make an agent in an environment good at a particular task. So you can imagine here that a car is driving around a track, and we'd ideally like it to stay on the track as much as possible and not wiggle off into the grass and not go around the track very fast. So what we need to do is we need to give the agent a reward every time it does something well. So in this case, it gets a reward every single time it drives over the track, and it doesn't get the reward when it drives off onto the grass. And then the agent receives that reward alongside the next state and has to make an action in the environment. And this cycle continues, and using reinforcement learning, we can ensure that the car gets very, very good at this particular task. Okay, so this isn't a particularly difficult problem in the car racing model example, but what they wanted to do in the world models paper was show actually something quite incredible, and I'll take you through this step by step as to how they did it and the different parts of the model. So this is the same diagram we've just seen, with the environment at the top giving the agent a particular state, which is S. And then what the agent does first of all is it encodes this state, this pixel grid of the track, into a latent space Z. So Z is now the latent representation of a particular frame that it's just received. A yellow world model box is essentially a recurrent neural network which takes this Z and tries to predict what the next Z will look like when it takes a particular action in the environment. So you can see here the inputs are Z and the previous action, and it's trying to predict what this next Z will be. And it does this via a recurrent neural network which has an internal hidden state H. And it is that state that is given to the controller. You can imagine H as kind of an internal understanding of what the current state of the environment is. And the controller simply takes this and tries to, it pushes this through a multi-layer neural network to output a particular action, where the action might be turn left, turn right, or press the accelerator, or any combination of those three. And this is what's given back to the environment, and the whole thing goes around again. So the environment takes that action, calculates mechanically what obviously happens to the track and the car, and gives the car back the next state. So when training this, what happens is that the variational autoencoder gets trained first. So here it's not really caring at all about driving around a track fast. It's simply trying to encode the pictures that it's receiving into the latent space in exactly the same way as we've just seen with the MNIST dataset. So that's trained up front. The world model is then trained to predict the evolution of these Z values, these latent vectors that are coming out. So it takes, in this case, a 32-dimensional vector Z and tries to predict what the next Z will be. So that's the second thing that's trained. And then the last thing to be trained is the controller, which simply replays over history all of the different state transitions that it's seen. And through an evolutionary algorithm called CMA-ES, it's effectively an evolutionary algorithm that builds lots of different variations of the controller and sees which one performs best in the environment. And those ones that perform best get to stay on to the next round, and effectively the whole system evolves over time to be as good at the task as it can find. So first of all, let's go through what each of these parts looks like. So you can see here the output from, on the left-hand side, this is the actual observations from the environment. And then on the right-hand side is the output from the decoder. So you can see that it's done a pretty good job here of encoding, first of all, into a latent space, and then decoding pretty much perfectly what the actual original observation was. So we can see that the variational autoencoder here has been trained well. And crucially, it can generate new observations, and this is what makes it really exciting. So by playing around with these different values of the Z vector, you can actually get the system to imagine different kinds of track that it's never seen before. And it's exactly like we were doing with the digits. By moving around this latent space now in 32 dimensions, we can show that there's the model has understood that the track is continuous, and that it might branch off to the left and to the right, and there's different ways of the track to kind of bend and move. And that means that it can imagine in its head what this track will do, what this track could do in the future. And so that's really what the world model's job is to take these latent Z vectors and try to predict over time how they evolve. Now, what's really exciting, I think, about this is that what they realized is that the world model itself can act as an environment, because after all, the world model is simply taking the latent vector Z, applying an action to it, and trying to predict what the next Z will be. But that is exactly what the environment is doing as well. It's just that the environment is doing it mechanically with rules of the physics of the environment, whereas the world model is being trained to, as much as it can, do this as well as it can with Z. So what they did was simply replace the whole environment structure with the world model itself, a copy of it, which they called the dream environment. So now, if we follow the flow round, the world model gives the agent a latent Z, and then on the bottom, another world model tries to predict what the future Z will be in the next time step. This is then passed to the controller, which takes an action in the environment, and again, the first copy of the environment, the world model, will give it the next Z. So what this means is that it is effectively, the agent is able to imagine in its head what the future will look like, given it just replays this this flow of the Z latent vector in its head. And perhaps an example actually is the best way to show this. So this is like the dream of the car, of the agent in the environment. This is not being played in the environment itself. It's simply just, imagine just going around and around this loop, and at each time step you just decode the Z value. So we're only decoding it so that we can see what's happening inside its head. The model doesn't obviously need to decode it when it's being trained, because the Z values are enough for it to understand what's going on. But just so we can see like how it's imagining things playing out in the future, we can decode the Z values using the decoder from the Variational Autoencoder. And so what we do here is instead of training in the real environment, what we can do is train in the dream environment, because it's doing everything that the original environment is doing anyway. And in fact, on the left-hand diagram, the reward is also modeled in exactly the same way. So it predicts basically what its next reward will be given the z's, as well as just predicting the z's and the future evolution of that. And when you train the model in the dream environment, what you find actually incredibly is that it performs even better than models that were trained in the real environment. And there's a few reasons for that. First of all, it's much faster, because you don't have to keep going back to the environment to fetch the next time step. It's much faster to actually pass the Z value through the neural network and find effectively what the next Z value will be than it is to ask the environment to calculate mechanically what the next state will be of the environment. And so that it means you can do a lot more training loops, and it means you can do a lot more, you can basically give it a lot more chance to learn from the environment, from the dream environment itself. And so one of the reasons I think this is really important is because it shows that learning can happen without a environment and without actual real life data on which to learn. And when we start thinking about concepts like artificial general intelligence, one of the key things I think that humans are kind of, and certainly other animal life as well, is adept at, is the ability to visualize and the ability to imagine and the ability to effectively to generate new things that it hasn't seen before and synthesize that information, which is exactly what was happening in the world model. When it was driving itself around that track, it certainly hasn't seen some of those examples before, but it understood enough about the physics of the real environment just through its own world model to understand what might happen in the future, and therefore learn from things that it's imagined rather than things that it's actually seen. And so I think this idea can help us certainly take some steps on the way towards artificial general intelligence. And obviously there's a lot more to it than that, but I think this is a key idea that needs to be explored more. And I want to again just kind of take you through my thinking on this, and obviously get your thoughts as well at the questions at the end of the talk. But one of the things when I was thinking about this is that came into my head that I found really curious was, well, what if we just go back to first principles again? What do we expect agents to do when we place them in these random fields of data that they're exposed to? And reinforcement learning says, well, we expect them to be able to learn from rewards and to output actions. So if I just give it enough rewards and I just tell it to make mistakes as much as possible and learn from that through the actions that it's taking, eventually it will get really good. And supervised learning says, well, I'll just give it lots of labeled data, and if I give it enough labeled data, then it will be able to predict more accurately in the future through the backpropagation algorithm in terms of deep learning. But actually, when you think about this, none of these things really exist in the real world. Nature isn't so kind as to give us rewards that are nicely packaged and to zeros and ones or continuous variables. Actions don't particularly exist either. When we move or when we speak or when we look a certain direction, these are not particularly well defined things that nature has given us, and certainly they're not something that we're told out of the box that we can do. Babies have to kind of explore the world for itself and realize what possible things that its body has that it can use to affect the environment. And similarly, there's certainly no labels on anything when we learn, and we don't really particularly make well-defined predictions about the future or indeed about objects that we see. We just seem to have this innate ability to pick up that there are groups, and then those groups we decide it's useful to us to give a label, rather than having a predefined set of labels onto which we're trying to predict. So that's the problem. In nature, none of these exist. So all of these algorithms that we've worked so hard to build, they're very hard to actually apply in anything except very restrictive environments and very well-defined closed systems. And so when you kind of take a step back and realize what we have to play with, and if we're trying to build something that's really learns in the same way that, say, a baby animal or a baby human would do, well, all that exists really is this field of data that we exist in. And therefore, when you think about it like that, the only thing that it can do is model the environment generatively. The only thing it can reward itself on really is its ability to do that, to be able to say, can I recreate somehow the data that I'm seeing? And if so, then maybe that gives me a slight advantage in the environment, and that advantage will mean that I am able to survive, and that kind of positive feedback could be something that benefits me in the long run. So having this internal world model that can generatively model the data that's being input is, I think, probably the only thing that we do as growing babies and animal infants. The only thing really that they have the ability to do is to model the world generatively, and by some miracle and somehow this is enough to start displaying intelligence, perhaps through mechanisms which we'll talk about in a second. But I just wanted to mention here as well that this isn't a new idea. This is something that's started to creep into academia in the last few years through a number of different channels. Firstly, in terms of machine learning and that sort of area, but more interestingly also in terms of neuroscience, and papers written specifically about brain structure and how the brain may start to model the world generatively, and finding areas of the brain that do in fact do this. So there's 3 examples here of some of those papers. But yeah, I mean, I just wanted to kind of speak as well about this idea of generative modeling in an environment, and ask, well, what could the agent be doing beyond just modeling generatively? There's obviously an idea here that a few people have talked about, which comes up, which is that rewards, labels, and actions exist, but they only exist within our own world model. They only exist within our own mind. They're not something given to us by the environment. And so therefore maybe a property of a world model is that it decides what it wants to choose as its rewards. It decides what it wants to label, and it decides what it wants to call an action. And so a system that performs well in an environment will be therefore a system that can choose rewards well. It's no good rewarding myself for things that ultimately don't benefit me in the long run. So there must be a way of generative modeling also being able to generate very, very useful rewards. And even more importantly, I think, is to be able to change those rewards over time. So what was useful yesterday may not be useful today. And the ability to be fluid in the way that it thinks about the concept of a reward rather than fixed, which is how most reinforcement learning algorithms still have the concept of a fixed environment given reward. And I think that's, for AGI and for generative artificial intelligence, I just think that's never going to work. We're not going to be able to train an agent in that way. It has to be auto-generated. So I wanted to just finish up really with some ideas around this and why I think this is the future going forwards. If you look at this video on the left, I mean, apart from just being generally adorable, this is a baby playing around with blocks, and I think really nicely demonstrates the auto reward mechanism going into overdrive. So when it's my interpretation of this is that the baby kind of sees that something that it imagined to be true in the environment is in fact true, and that is enough for it to want to take this action again and again, because the baby here seems to be rewarding itself for achieving something in the environment which it knows should have been true and indeed is true. And there's the environment here isn't rewarding the baby for placing blocks on top of each other. It seems to be a purely kind of ecstatic emotion from within the system itself, i.e. the baby's brain, that obviously through evolution and through the years over which we've developed as humans has been a very useful property to have, that our brains can do this. And you know, therefore I think there's no better way really of summarizing this than one of Richard Feynman's quotes, which is that what I cannot create I do not understand. The ability to create and the ability to generate our own environment is for me the core concept that we need to explore more in artificial general intelligence. And indeed, a twist on this might be what AI cannot create, AI does not understand, and I think that's more true than ever. So thank you very much for listening. It's been a pleasure speaking to you all, or certainly speaking to you all from the past, and in a moment I think I'm going to be coming on your screen to answer some questions. So thank you again. I hope you enjoy the rest of the conference. Please do find me on Twitter and LinkedIn. I'm very happy to pick up any conversations offline as well, and have a great rest of the day. So thank you very much.
Fantastic. Okay, well, thank you very much, David, for that very awesome talk. A lot of interesting theories there, a lot of interesting practice too, and I'm sure our viewers have enjoyed that thoroughly. And I know we have a few questions. David, are you with us?
Hey, yeah, can you hear me okay?
Better, much better, much better. Okay. Thank you so much. Okay, so awesome. Really interesting, especially the last part around sort of the reward mechanisms and how the baby was getting satisfaction from the environment, from its achievements. I often wonder how careful we need to be with the AI so that it receives the right kind of rewards, the right kind of satisfaction if it's self-learning. But I'm not an expert, so I won't delve too much into that. Let's go directly to questions. The first question I have is, nice presentation. Does training always happen in 2 dimensions?
Yeah, thanks for your question. No, not at all. In fact, in the world model environment we saw there was a 32-dimensional latent space, which it sounds a lot, but actually it's very small in comparison to the pixel space that it's trying to represent, which was in many more dimensions than that, because it's obviously every single pixel is its own dimension. So no, it can be many more than that. It's just that for the toy example we used 2.
Fantastic. Okay, thank you. And then the next question we have, let's say you talk to a 5-year-old child. Can you explain in simple words the difference between deterministic and probabilistic terms?
Yeah, I mean, I would say probably, used probably there, so I probably shouldn't use that word. Deterministic is where the outcome is fixed. So given something happens, that you can guarantee something else happens. Whereas I guess probabilistic would be described as there could be many possible things that can happen, each of which has a certain probability attached to it. Or if I was speaking to a 5-year-old child, perhaps you would use things like the probability of them being able to play with their toys later if they tidy up the ones that they've already used.
Fantastic, thank you. And one final question very quickly, because our next speaker needs to jump on at 6 exactly. Hello, David. I'd like to ask, what was the inspiration for writing the book?
Well, yeah, I mean, it's something that's always fascinated me. And I kind of thought to myself, well, what might be the next sort of big thing for machine learning? Because it's no good writing a book about something that's already big. It'll be too late by the time, because things move so fast these days. So, I mean, I was looking at what was coming out, and a lot of the papers were starting to talk about the idea of generative deep learning. And I felt like there was an opportunity to publish something that summarized all of the different advancements in the field so far.
Well, thank you so much. Well, thank you so much. It's a great book, and I'm sure everyone's thoroughly enjoying it. Thank you so much for being part of the conference of Open 2020 here, directly from Athens, and we hope to welcome you in Athens at some point in the near future. Enjoy the rest of your conference. Thank you.
Thanks very much.